In this section, we're going to simplify square roots, not enter them into the calculator and get the decimal and then have to round the answer. Our answers are actually going to be what we call simplified. And the square root of 32 simplifies to 4 times the square root of 2. By the end of this section, you're going to learn how to turn this into something that looks like this. It's actually a fairly straightforward process. You just got to learn how to do it, and then from then on, you're going to use it next year in geometry, and we use it all the time in Algebra 2 and anything beyond that all the time. So this is a skill that you need to have. It's also all over the ACT test. We will not be using the calculator to estimate or approximate roots in this section because approximations are not exact answers. And in math, we like exact answers. So like the square root of 4 square root 2 is the exact answer. The decimal approximation, 5 point whatever it is, 7 something, that's an approximation. You're rounding. It's an estimate. This is exact, and that's the answer we're looking for. So do not give me decimal answers in this section unless it specifically says that you can do so. To simplify roots, there's only 3 easy rules that you have to follow. These rules must be met before you can call an answer simplified. First rule, no number inside the radical have factors that are perfect squares. So before we go on, actually, let's talk about the perfect squares. Let's make that list of perfect squares again so that we have it fresh in our minds. Where do we start? 1 is the first perfect square because 1 times 1 is 1. So we have 1, which is 1 times 1. What's the next one? 2 times 2 is 4, so 2 times 2 is 4. 4 is a perfect square. What's the next one? 3 times 3 is 9, so 3 times 3 is 9. 9 is a perfect square. What's the next perfect square? 16, and then, so that is 4 times 4. What's the next one? 25, that's 5 times 5. 36, okay. 64, 81, 100. What is this one? 10 times 10. 11 times 11? 121. 144. 169. That's what times what? 13 times 13. Next one? Yep. So that's 13 times 13. 14 times 14 is 196, and I'm almost out of room, so let's do one more. 15 times 15, 225. And like I've said before, this up to here, 1 through 100 perfect squares, these are the ones that you have to recognize immediately. These ones down here you should also know because they're the ones that pop up most often on your map test or whatever, okay? So these are easy ones to recognize also, you just got to remember that they're there. And you can keep going, 16 times 16, 17 times 17, and so on, okay? But these are the ones that pop up the most. So, no numbers inside the radicals have factors that are perfect squares. So, factors, remember, are numbers that multiply together to give me something. So, if I take the number 48, is there a perfect square that's a factor of 48? The answer is yes. 16 times 3 is 48. 16 is a perfect square. So that's what I'm talking about with number 1. Number 2, no numbers inside radicals are fractions. So this, the square root of 1/2, is not simplified. And we'll have to learn how to take care of that. This, you'll hear me say this is rude here. There's a reason why it's rude. Number 3, no roots in the denominator. So if I had something like 3 divided by the square root of 2, that is also just like this one. This is considered rude. You can't have a square root in the denominator. And we'll learn how to take care of that also. So those are the 3 rules that you have to follow before any of your square roots are simplified. Now, the first property we're going to work on is the multiplication property of square roots. It's a very easy one. If I have a square root, I can split that square root into 2 littler square roots that are being multiplied together. So like my example up here of 48. 48 is 16 times 3. So I can split 48 into 16 times 3 and write it as two separate square roots. So the process for that looks like this. If I have the square root of 48, I'm going to split 48 into 16 times 3. So this turns into the square root of 16 times 3. And then I can split that again into the square root of 16 times the square root of 3. And that's what they're saying right here. Now, once I've done that, what is the square root of 16? It's 4. What is the square root of 3? Well, 3 isn't a perfect square, so I can't take the square root of it, which means I just leave it, the square root of 3. So I take the square root of 16 and I get 4, and it's times the square root of 3, and that's my answer. So that is how you simplify square roots. So let's take a look at the square root of 80. We want to find the biggest perfect square, not just a perfect square, but the biggest perfect square that goes into 80. Okay, 40 is not a perfect square. So if you don't know the biggest perfect square that goes into it, there's a couple ways you can do this. There's a long way and a short way. I'll show you the long way, and then I'm going to show you the short way so that you can do this faster. What you can do is you can do remember the prime factorization tree, like the cake or the tree? Start with prime numbers that go into 80. The smallest prime number that goes into 80 is 2. So here's my 80, and I have 2, and I'm left with 40. And then 2 goes into 40 20 times, and then 2 goes into 20 10 times, and then 2 goes into 10 5 times. 5 is prime, so I'm done. Now what you're going to do is multiply together all your pairs. So we have a pair of 2's here. We have another pair of 2's here. And since I circled all those pairs, I'm going to multiply all these numbers together. 2 times 2 times 2 times 2 is 16. 16 times 5 gives me 80. So I'm going to split this into the square root of 16 times 5. 16 is the biggest perfect square that goes into 80. Now I can split this into two separate square roots. The square root of 16 times the square root of 5. And the square root of 16, of course, is 4. So this part turns into 4. This part I can't do anything with, so I just leave it square root 5. So my answer is 4 root 5. And I'm done. Sometimes it's faster to avoid doing this and just start going through your list of perfect squares. If you have a calculator sitting in front of you, you could take 80 and divide it by perfect squares that are smaller than 80. So you could do 64, that's not going to work. 49 doesn't work. 36 doesn't work. 80 divided by 25 doesn't work. 80 divided by 16, you get 5. That's the first perfect square less than 80 that goes into 80. So therefore 16 times 5 is what you're going to split it into. That process is a little bit faster sometimes. So now we want to take the square root of 54. Is there a perfect square that goes into 54? 9 does. 9 times what is 54? 6. Okay, now think about it. Think about 6. Is there a perfect square that goes into 6 nicely? 3 goes into 6 2 times, but neither of those is a perfect square. So that's it, right? That means 9 is my biggest perfect square that goes into 54. So I'm going to turn this into the square root of 9 times, what did we say? 6, okay? And then what do I do? So yeah, I could split this into two square roots, square root of 9 times the square root of 6. If you already saw that the square root of 9 is 3 and you just wanted to do it that way, that's fine. Square root of 9 is 3 times the square root of 6, and you're done. All right, same idea for the square root of 180. Go ahead. All right, we can multiply roots together. Just like we, on the last page, we're taking roots apart, splitting them into the square root of a perfect square times some other number. We can multiply square roots together. Here are the rules for multiplying roots together. It is legal to do, but you have to follow these 4 rules. The things inside the roots multiply together. So if you have stuff under a square root times some stuff under a square root, you can multiply the stuff under the square root together, and they stay inside the square root. The things outside the roots multiply together. So if I had 2 root 5 times 4 root 3 or something. The 2 and the 4, the things that were outside, those multiply together also. But they stay outside the square root. It's sort of like Vegas. Things that happen outside of the square root stay outside the square root. Things that happen inside the square root stay inside the square root. Kind of like Vegas. What happens in Vegas stays in Vegas. Okay? Number 3, things... Yeah, that probably would come back with you. Things outside do not multiply with things inside, and that's the Vegas thing that I was just talking about. If they're outside, they multiply together. If they're inside, they multiply together. If they're in 2 separate places, they do not multiply together. So things outside stay outside. Roots must be simplified after multiplying. So you can do this, but then remember what we just learned. You always have to simplify the root once it's done. It's kind of like when you're adding or subtracting fractions or whatever. You always reduce your fraction. You always simplify the square root also. So, for example, we have the square root of 2 times the square root of 14. Well, we have numbers inside the square roots there, so we can multiply those numbers together. This becomes the square root of what? Yeah, what's 2 times 14? 28. So now we have the square root of 28. Those 2 things were under the square root. We can multiply them together, and they stay under the square root. Now, we have to simplify the square root of 28. Is there a perfect square that goes into 28? 7 times what? 4. 4 is a perfect square that goes into 28. 7 times. That's the biggest perfect square that goes into 28, so I'm going to write the square root of 4 times 7. No, it doesn't. The square root of 4 times 7 gives me the square root of 4 times the square root of 7. The square root of 4 is 2. The square root of 7 I can't take, so my answer is 2 root 7. And I'm done. So we've added one more step here. We can multiply this stuff together. All right, let me do the one below because it's different. The things that are outside multiply together. So I have a 2 outside times a 3 outside, which turns into 6. And now I have the square root of the things inside multiply together. This turns into 50. So now I have 6 root 50. What do I need to do next? Yeah, see if this square root thing simplifies. Is there a perfect square that goes into 50? 25 times 2. So now this turns into 6 times the square root of 25 times 2, which we can then split into 6 square root 25 times the square root of 2, and the square root of 25 is 5. So now we have 6 times 5 times the square root of 2, and 6 times 5 is 30, square root 2. That's your answer. For the square root of 5 times the square root of 10, what do we do? And we get square root 50. Does that simplify? 25 times 2. 25 is a perfect square. So this becomes square root 25, square root 2. Square root of 25 is 5, square root 2. That's the answer. What's the next one going to be? So square root of 48. And does that simplify? So 4 times 12 is 48, but that's not the biggest perfect square that goes into 48. What's the biggest one? 16 and 3, yeah. So the square root of 16 times 3, which I can split into the square root of 16 times the square root of 3, which is 4 square root 3, 4 root 3. If you noticed on this one compared to this one, I skipped this step right here. If you want to do that, that's fine. If you write this step and you want to skip this step and go straight to the answer, that's fine too. The more practice you have with this, the faster you're going to get to the point where you'll be able to actually skip all of this work and just go straight to the answer. That'll probably be about the time you get to Algebra 2. This one, what do we do? Yeah, remember, anytime you have something with no number in front of it, like this right here, there's actually a 1 right there. So we have 5 times 1, which is 5, and then the square root of 36. Is there a perfect square that goes into 36? 36 is a perfect square. So actually we're staring at a perfect square here. This turns into 5 times what? Times 6, which is 30. So the square root actually disappeared on that one, and that's fine, that can happen. On the last one, what do we get? So we have 3 times 2 outside, so 6 square root 4. The square root of 4 is not 4, it's 2. So this turns into 6 times 2, which is 12. We're multiplying. 6 times 2 is 12. So that's how you do this sort of thing. What's outside stays outside. What's inside stays inside. But you can multiply them together. Once you multiply square roots together, you have to simplify the square root. And even though this one couldn't be simplified here, and this one couldn't be simplified here, once we multiply them together, it could be simplified. So you have to watch for that. All right, the next thing we're looking at is dividing roots. Just like multiplying roots, we can divide roots, and the rules are very similar between the two. It's legal to divide roots following these rules. First of all, reduce all fractions. Always reduce all fractions. No roots can be left in the denominator. That's rude. It's actually considered like bad manners. It's rude if you leave a square root in the denominator. There's a reason for that mathematically. Things outside the roots, just like with multiplication, things outside the roots can be divided or reduced, and they stay outside the square root symbol. Things inside the roots can also be divided or reduced, and they stay inside the radical, the square root symbol. This is the big one here. A big root with a fraction can be split into 2 little roots and vice versa. So if I have a big square root of a fraction, something divided by something underneath the square root, I can split that into 2 little square roots being divided. So the square root of this big fraction turns into the square root of the numerator divided by the square root of the denominator. I can go this way, and I can also go the other way. If I have 2 square roots that are being divided, I can turn that into one big square root of a fraction. So that property is pretty important. We use it all the time. And we can also combine dividing and multiplying. So we can have, like in this last one right here, we have 2 square roots that are being multiplied together. But within the multiplication, there is division going on. So we can mix and match. We can do all kinds of things here. For the first one, simplify the square root of 35 divided by 15. What should we do first, probably? Yeah, reduce the fraction. Notice rule number 1 is reduce the fraction. So you can reduce the fraction. This becomes the square root of, we have a GCF top and bottom of 5. So if I divide the top by 5, I get 7. Divide the bottom by 5, and I get 3. So this is the square root of 7/3. No. Now, we have this big fraction here, turning it into a little one divided by a little one. That's going to turn into the square root of 7 divided by the square root of 3. Now, notice number 2's rule. No roots can be left in the denominator. That's rude. Do we have a root in the denominator right now? Yeah, we do. So we're actually being very rude. This would be like if you were sitting down at the dinner table and you put your feet up right next to the mashed potatoes. Would your family be very happy about that? Probably not. Not really, okay? So that's pretty rude. This is pretty rude also in math. We can't leave that square root in the denominator. To get rid of that square root in the denominator, we have to do something very special. It's called rationalizing the denominator. You don't need to know that. What you need to know is that what you're going to do is multiply by a fancy 1 to get rid of the denominator, square root in the denominator, okay? So we're multiplying by a fancy 1 here. The fancy 1 is going to let us get rid of the square root in the denominator. And it's very easy to do. All you have to do is multiply top and bottom by the square root that you're looking at. Because the square root of something times itself let me, like off to the side here, let me do this. If I have the square root of a times the square root of a, I would get the square root of a squared. And if I square root something that's being squared, what happens? It just turns into that number there, the base, right? If I square root x squared, I get x, right? So if I square root a squared, don't I get a? If I square root 3 squared, don't I get 3? Okay, yes you do. So the square root of 3 is my fancy one. Watch what happens. Multiply across. What's the square root of 3 times the square root of 3? It's the square root of... So how do you do this? We have two numbers being multiplied inside the square root, so 3 times 3 is 9. The square root of 9 is 3. So that made the square root in the denominator disappear. So we have the square root of 9 now in the denominator. In the numerator, the square root of 7 times the square root of 3 is the square root of 21. And now we have the square root of 9, which is 3. The square root disappeared. We're not being root anymore. The square root of 21 doesn't simplify, so it just stays the square root of 21. That's the answer. The first time seeing this, you're going to be probably a little confused, and that's okay. Practicing a little bit, this will be a piece of cake. On this second one, I'm going to use a couple different rules here. First, I'm going to use this rule. Notice that I have a little square root divided by a little square root. The first thing I'm going to do is this rule. I'm going to go this way, from here to here. So I'm going to turn this into a big square root. Big square root of 6 over 12. So now I have 6/12 under that square root. What could I do to that 6/12? Reduce it. Yeah, what does it turn into? 1/2. So now I have a big square root of 1/2. That just makes my numbers a little bit easier to work with. Now I'm going to go back. I'm going to undo this big square root and turn it into two little square roots. When I do that, I have the square root of 1 divided by the square root of 2. That is rude. But what's the square root of 1 first? It's 1. So that becomes 1 divided by the square root of 2. And I'm being rude here. I have the square root in the denominator. So what do I need to do? Multiply by a fancy 1. And the fancy 1 will be the square root of 2, somebody said. So that's right. 1 times the square root of 2 is the square root of 2, divided by the square root of 2 times the square root of 2, which is the square root of 4, and the square root of 4 is 2. That's your answer. On this last one, you have a couple different ways you could go. One's going to take a lot longer than the other. Anybody have an idea of what we should do first? Yes. Yeah. Remember the rule from the last thing where we were multiplying square roots together? That's what's happening here. We're multiplying square roots together, which means I can multiply this number times this number, which means I have two fractions here that can be multiplied together. How do I multiply fractions? Multiply across. Okay? So I'm going to have a big square root still, but now I multiply across, and 3 times 9 is 27. Divided by 16 times 5, which is 80? I think so too. So now we have the square root of 27 eightieths. So split it into 2. We have the square root of 27 divided by the square root of 80. That is rude, but I want to reduce these first. Is there a perfect square that goes into 27? 9 and 3. So the square root of 27 will turn into the square root of 9 times 3. Divided by, is there a perfect square that goes into 80? 16 times 5. Yeah, actually, there was the perfect square right there. 16 times 5. So this splits into the square root of 16 times 5. Okay, in the top, that simplifies to what? 3, square root 3 is correct. And the bottom simplifies to what? 4 square root 5. Yeah, this is rude here. We have a square root in the denominator, which we can't have. How do I get rid of that square root in the denominator? The fancy one will be, not 5, square root 5. So I'm out of room here. I'm going to write this down over here. 3 square root 3 over 4 square root 5. And we said my fancy one needs to be the square root of 5. Okay, in the numerator we have 3 times 1, which is 3. Square root 15. Square root of 3 times square root of 5 is square root of 15, divided by square root of 5 times the square root of 5 is the square root of 25, which is 5. So that's 4 times 5, which is 20. Does 3/20 reduce? No. Does the square root of 15 simplify? Is there a perfect square that goes into 15? 3 times 5. Neither of those works. So square root of 15 does not simplify. The fraction does not reduce. So that is the answer. Like I said, there's a couple different ways you can go about this one. This is the route we chose. A couple of other ways you could have simplified this first, and then multiplied across. That would be another way to do it. Yes? We can also simplify square roots involving variables if we write them as an even power times what's left over. So that's kind of weird, awkward wording. What I'm trying to say is x squared a perfect square? What times what gives me x squared? What times itself gives me x squared? Yeah, x times x gives me x squared. So is x squared a perfect square? Yes. Is x to the 4th power a perfect square? Does something times itself give me x to the 4th power? Yeah, x squared times x squared gives me x to the 4th power. Is x to the 6th power a perfect square? X to the 3rd times itself gives you x to the 6th. So x to the 6th is also a perfect square. So x squared is a perfect square, x to the 4th is a perfect square, x to the 6th is a perfect square. Is x to the 8th a perfect square? X to the 4th times x to the 4th. You add the exponents when you multiply like bases. Remember that? What about x to the 10th? X to the 12th? What am I doing with my exponents? Even number exponents are perfect squares. So if you keep that in mind, you can turn this into a perfect square times what's left over. Just like we were doing before with like the square root of 48. Turns into the square root of 16 times what's left over, which is 3. The square root of x to the 3rd turns into the square root of x squared times what's left over, which is x. And now the square root of x squared is what? X. And I'm left with the square root of x. Good. So that's what you're going to be able to do on problems like this. If you look at this one, we have the square root of 54 n to the 7th. We're still going to treat the 54 by finding the biggest perfect square that goes into 54, which is 9. And the biggest perfect square that goes into n to the 7th is n to the 6th. So you're looking for the biggest even number that's lower than that number. That would be 6. So this turns into the square root of 54 will turn into 9 times 6. N to the 7th will turn into n to the 6th times n. And now you're going to take the square root of everything you can take the square root of, leave everything that you can't take the square root of underneath the square root symbol, and you're done. So the square root of 9 is 3. Can I take the square root of 6? No. Can I take the square root of n to the 6th? Yeah, what do I get? N to the 3rd, because n to the 3rd times n to the 3rd, you add the exponents, you get n to the 6th. All right, can I take the square root of n? No, so now I need to write square root, what's left over? 6n, and you're done. Good. You like it better with variables? All right, the third one. What? Why not? What can we do on the third one? All right, we have the negative m out front. We have the square root symbol. What's the biggest perfect square that goes into 80? 16 times 5. So the 80 splits into 16 times 5 times, what's the biggest perfect square that goes into m to the 9th? M to the 8th times m. Okay, so now we have the negative m still, times 4 m to the 4th, because I can take the square root of 16 and I get 4. I can take the square root of m to the 8th and I get m to the 4th. Square root, what's left over is the 5 and the m. We can't take the negative away, but we can multiply like terms here. M times m to the 4th is m to the what? Negative m to the 1st times m to the 4th is negative m to the 5th. So we have negative m to the 5th, that 4, square root symbol, 5m. That is the answer. For the division type of problem, let's take a look at this one. We have a big square root of 36a divided by 4a to the 3rd. Again, you can reduce your fraction. So this becomes the big square root of, what's 36 divided by 4? 36 divided by 4 is 9. And then we have a divided by a to the 3rd. When you have like bases, you subtract exponents if you're dividing. So a divided by a to the 3rd becomes a to the negative 2nd power. And hopefully remember what we do with negative exponents. They go in the denominator. So this is the square root of 9 divided by a squared. So now I can split that into two little square roots. Square root of 9 over the square root of a squared. And the square root of 9 is 3. The square root of a squared is a. So my answer is 3 divided by a. You can do the other two very similarly. Just make sure you're not leaving square roots in the denominator because that's rude.